Hello everybody. Today we are going to be starting a unit on the gases. If you recall, there are three main states of matter that we've talked about, and then we have the solid, the liquid, and the gas state. And if you recall, if you look at this diagram, over on the right, you notice that solids are very organized. The particles are right next to each other. They have a definite shape. They have a definite volume. And in terms of kinetic energy, they have very low kinetic energy. What solids do is they simply are fixed in positions and they vibrate in place, but they do have kinetic energy. As you heat a gas, as you heat a solid and it melts into a liquid, you'll notice that in the liquid state, the particles are a little bit more scattered. They do have freedom to move around. They don't have a shape. What gives a liquid its shape is the container it's being held in. However, they do have a definite volume. You can actually measure exactly 1 milliliter of water or 1 gallon of water. You can obtain an exact volume of a liquid. And as far as kinetic energy, it has a little bit more kinetic energy than the solid phase. It's moving a little faster. It has enough energy so that they can particles can scatter a little bit further apart, but they're still relatively close to one another, but not as close as a solid. Then if you continue to heat a liquid, what's going to happen is the particles are going to spread out. You're going to now vaporize or boil or evaporate, and these particles will now enter the gas state. And if you look at the gas state, gases are very disorganized. They are all over the place. Notice the distance between the particles. They're very far from each other. They have no shape, no volume, and in terms of kinetic energy, they have very high kinetic energy, which means that they are moving much faster than the particles in the liquid or in the solid phase. Out of these three states of matter, what we're going to do is we're going to focus on the gas phase. If you look at section 11.2, we're going to talk theoretically today about a model that describes the behavior of gases, and it's known as the kinetic molecular theory. It is based on the idea that particles of matter are always in motion, and because of this motion has consequences. So what we're going to do is we're going to talk about 6 assumptions that make up the kinetic molecular theory of gases. The first assumption is going to be that gases are very small particles, and each of these particles has mass. You will see me diagram, let's say a container here. These particles are tiny. Notice how small I'm making the gas particles, and you will also notice that I am making these particles far apart from each other, okay? And they each have mass. In fact, we'll talk about this a little bit later because that's also a physical property of gases. You'll see that some gas molecules have less mass than others. For instance, hydrogen is the lightest gas known to man. Hydrogen, because it's diatomic, if you remember, the atomic mass for hydrogen would be approximately 2 AMU, okay, from the periodic table. If you get a heavier gas, such as oxygen gas, and that one is also diatomic, you'll see that that one is approximately 32 AMU. So the gases do have their own masses, and they are relatively small. The second property here that you'll see that we're going to assume is that gases have a volume equal to 0. Okay, if you notice in this, and the particles here in this diagram, they're kind of large, the way they're drawn here compared to the container. I'm going to go back a minute to my drawing over here, and if you notice, I'm going to draw just a couple of gas molecules, and notice that most of the volume here is empty space. If you compare the volume occupied by a single gas molecule compared to the volume of the remainder of the container, the volume of a gas is approximately zero. Okay, so we're going to assume that the volume of a gas is zero. It's not zero, it's very little, but it's negligible. And that is because the actual volume occupied by a gas is relatively small compared to the volume of the container. Notice all the space, empty space. That's where most of the volume occurs, and none of that volume consists of gas particles. So this is going to be our second assumption using this model here. The third one is that, since this is kinetic energy and gases have a lot of kinetic energy, they're constantly moving. Now, I'm going to describe the way they move. Two things. First, they move in straight lines and they can move in any direction. And that's what I mean by random directions. If we look over here, these particles, whichever way they decide to move, they're going to move in a straight line. So let's say this one's moving this way. This one's moving over here. This one's moving over here. It doesn't matter which way they are moving because they can move randomly. What does matter is that they do move in straight lines. Okay, so that's a description of the way they move. They're in constant motion. Now, as they're moving, this is what's going to happen. Two things can happen as particles are moving. A, they can either collide with each other, or B, they can collide against the wall of the container. Now, there are two types of collisions. One is called an elastic collision, and another is called an inelastic collision. Those are two types of collisions that exist. I'm going to tell you the difference between the two, but notice how elastic collisions has been underlined because the collisions that gas exhibit are of the elastic variety. So when molecules are moving around, we know they move in straight lines. So let's say I'm going to draw a molecule here. If this molecule were to bump into this one, it's going to simply turn and change direction. And whatever direction that is depends on the angle of the impact. For instance, if it hits the wall of the container here, depending on that angle, when it bounces off, it's going to also change direction, but it will still be in a straight line. So molecules can either hit each other, as you saw here, or they can hit the wall of the container. Now let's talk about the two types of collisions. The inelastic collision, an example that I like to use is, imagine you're playing pool and you have ball A and you have here the little pool stick, okay? Let's put a little chalk here, and with the stick, we're going to hit ball A, and our objective is to hit ball B over here. So ball A gets hit, ball A is moving, and when ball A hits ball B, what ends up happening is ball A will stop here, and ball B will move. What just happened is whatever kinetic energy ball A had, it transferred that kinetic energy to ball B. Ball A is either going to slow down or stop completely. Let's say it stopped completely. And ball B will accept whatever that kinetic energy was. It will get transferred from A to B, and then B will then move a certain distance. Now, the collision that I just described, where kinetic energy is transferred from one particle to another, is called an inelastic collision. Gases do not do this. What gases do is they do elastic collisions. Going back to our picture here, every time a gas particle hits another particle or the wall of the container, it does not gain nor lose kinetic energy. It simply hits and bounces off. There is no transfer of kinetic energy. It keeps the kinetic energy it has. The only thing that happens is that it changes directions. So think of the word elastic like if these particles were bouncing off each other. And that's basically the type of collisions that are happening within this container. They are elastic collisions. Okay? Now, if you look here, there is also a relationship between temperature and kinetic energy. Okay? So if you look at this definition, it says that the average kinetic energy of the particles of a gas is directly proportional to the Kelvin temperature. What that means is that if I were to increase the temperature, what that will do is it will cause the gas particles to move faster. So the velocity will increase. And kinetic energy is a measure of velocity. So the faster that molecules are moving, the more kinetic energy that they possess. So when you increase temperature, what you're doing is you're increasing the speed at which these molecules move, which essentially means you're increasing the kinetic energy. Here is, in physics, this is the equation that we use to find kinetic energy. It's equal to half times the mass of the object times the velocity of the object squared. When you multiply those factors together, that's how you calculate kinetic energy. So on the bottom here it says that an increase in temperature will increase the velocity of a gas. Therefore, an increase in velocity increases the kinetic energy. And conversely, if the temperature goes down, then the molecules start to move slower. And if they're moving slower, they're going to have lower kinetic energy. So this relationship, they are directly proportional to each other. Now, here is one more thing we're going to talk about in this assumption. It says here that there are no forces of attraction or repulsion between the particles of a gas. This is not totally true. Okay? When we saw earlier a solid, the particles in a solid, they're very close to each other. When you look at a gas, the particles of a gas, they're very far apart from each other. So, the assumption that we're making here, we're assuming that there are no forces of attraction or repulsion. The assumption is based on the distance between gas particles. You see, we're going to assume that the particles are so far apart from each other that they don't have the ability to interact with each other. Now, in the real world, that's not true. Gases can attract, they can repel. There are forces of attraction or repulsion, but they're very weak. And they're very weak because the particles are so far from each other that they don't really have a chance to interact. Since they're so weak, we're going to assume that they don't have any forces of attraction or repulsion. So this is one of the assumptions, that besides gases having no volume, we also assume that gases exhibit no forces of attraction nor repulsion. Okay? So those were the 6 kinetic molecular theory assumptions. And this other part here that I'm going to show you is some physical properties that gases have. Earlier, I told you that gases have mass, and if you recall, I mentioned how hydrogen gas, being diatomic, has a mass of approximately 2 AMU. This is the lightest gas known to man. Helium is the second lightest gas. If you look at the periodic table, it has an atomic mass unit of approximately 4. We saw how oxygen is about 32 AMU. Okay, that one's also diatomic. Maybe it's carbon dioxide. Carbon dioxide is a heavier gas. That one is about 44.01 AMU. So that one's a little heavier. So gases do have mass. Okay? Think of a tire. When you remove the air from a tire, the tire will weigh less. Okay? Because you've removed air from that tire, and if you measure the tire, the mass before and after, you will see that the mass after it's been deflated will be lower because gases do have mass. Second, gases are compressible. Okay? Notice that compressible means that they can be squeezed into a smaller volume. So imagine squeezing a container or a balloon. If a balloon or a container has gases inside, they can be compressed. Now notice that it says here liquids and solids are not compressible. The reason is because the particles of a liquid and a solid, they're so close to each other that there's no way to bring them any closer together. Whereas gases, if you remember the picture that I showed you, the spaces between the gases, there's a lot of space between them. So there's a lot of room to squeeze those particles and bring them closer to each other. That's why gases are compressible. If you look at this picture on the left here, notice the distance on the left between the red particles. And if you look at the container, this is like a piston, and the container is being squeezed, as you could see on the second picture here. Notice the arrow going down, and notice how as you reduce the volume, you're bringing the particles closer to each other. I'm showing you here how gases are being compressed as the particles are being brought closer to each other. Now, when you look at on the right side and you look at a liquid over here, notice there's very little space between liquids, and the same applies for solids. You can't compress it. There's no room to bring liquids and solids any closer together than what they already are. So the only ones that are compressible are the gases. Now, expansion. Let's say you open up a perfume bottle. In a few seconds, anyone in the room might be able to smell the perfume. See, gases have the ability to fill the entire volume of a container. In my example, the container could be a room, okay? Or it could be a smaller container. When you put a gas in a container, it will expand and it will spread out and fill whatever size of that container is. Now recall that gases are not organized at all. They have no shape and no volume. They have that freedom to be able to spread out and to expand. So expansion is number 3. Fluidity is number 4. And if you look at the definition of what fluidity is, a fluid basically is when a particle can glide or move past another particle. And gas particles can definitely glide past each other. They can just move back and forth. We all know liquids can do this too. Liquids have the freedom to glide past each other. So if you look at the strict definition of what a fluid is, since both gases and liquids can glide past each other, both of them are referred to as fluids. A lot of people think that fluids is unique to liquids. No, gases also, since they fit the description that the particles can glide past each other, they're also considered fluids. Now, you may recall that gases have something very unique that they can do. Well, not unique. Liquids can do this too, but at a slower rate. And that is called diffusion. You perhaps remember from biology class that diffusion is the movement of a substance from an area of high concentration to an area of low concentration. In my example that I mentioned earlier, if I open up a perfume bottle, the perfume bottle has a high concentration of gas molecules. The rest of the room, there's no perfume. It has low concentration. Immediately after I open the container, the gases will just exit the container and start to diffuse and spread throughout the room. And the reason for that is because they are going from an area of high concentration, the perfume bottle, to an area of low concentration, which would be the remainder of the room. In the definition that I wrote here, I put diffusion is the gradual mixing of two substances because of their spontaneous random motion. Gases can do this because they spontaneously are just moving randomly in all directions, and the minute that you open a container, they have the freedom to move out of the container and into an area where there is a lower concentration, and that will give them the ability to diffuse. So this is diffusion here with fluidity. Okay? And then we got, this is an important one, gases exert pressure. A little while ago, I drew a container and I drew a few particles. And notice I'm drawing a few particles here, random, spread apart. And there's a conceptual definition of pressure that is very important. Well, we're going to be talking about pressure a little bit more in more detail and how to convert from one pressure unit to another. But pressure in a conceptual sense has to do with the number of collisions. We talked about there are two types of collisions. Particles can either collide with each other. So let's say I have a particle here colliding and changing directions. Or I can have a particle over here hitting the wall of the container and then changing directions. I can have another particle over here hitting the wall of the container and changing directions. Whatever that may be, okay? So as these particles are colliding, every time that they collide against the wall of the container, and as well as, they collide with each other, but more importantly, every time that these particles collide against the wall of the container, that is what we call pressure. So if the number of collisions increases, that means that the pressure increases. So I'm going to write that down. If the number of collisions goes up, the pressure will also go up, because pressure is really a measure of collisions between these particles and the wall of the container. So gases do have the ability to exert pressure. Now, this one's going to be easy to explain. See, the pressure of a gas also depends on temperature. So if you think about this, we have the same container, and a little while ago I mentioned that if I increase the temperature, the molecules start moving faster. Their velocity increases, which means they now have more kinetic energy. Okay? So the faster that these particles are moving, the more often they're going to hit the wall of the container. See, when you increase temperature, what you're going to end up doing is you're going to increase the number of collisions. And if you increase the number of collisions, that means that there is going to be more pressure. So pressure and temperature are directly proportional, because when temperature is increased, there are more collisions, and because the particles are moving faster, so they're going to collide more often and with more momentum. Since they are moving faster, they also will hit the container with more force. So when you combine those two factors, the increasing number of collisions and the impact of the force, you're basically increasing the pressure when you raise the temperature. And then we have one more concept, which has to do with density. And I know mathematically density has to do with mass divided by volume, but I'm going to give you a conceptual definition of density. You see, density has to do with how compact particles are. If you recall, in a solid, all the molecules are very, very close to each other. That's a solid. So in a solid, you have a very high density. When a solid melts and becomes a liquid, let me draw a little container here, the particles are slightly scattered, just a little bit. Okay, so they have more in the liquid phase, they have more of a medium density, or a less, they're not as dense as a solid. Notice in a solid, everybody's nice and compact, very, very dense. But look what happens when we compare solids with, let's say, a gas. So here I got a container. I'm going to make it a little bigger. I'm going to put here G for gas, and I'm going to draw some particles. And I want you to analyze the distance between those particles. Notice they are not compact. They are very spread apart. So when you compact particles, like in the solid state, you have a very high density. But when particles are spread apart, like in the gas phase, and they are not compact at all, they're very spread apart from each other, that's why gases are going to have a very low density, because the particles are very spread apart. So in general, gases do exhibit low densities. Okay? And those were the 7 physical properties of gases. We will be moving on to pressure as our next topic.